Hello students, welcome back. Let us continue discussing hypothesis testing, continued from lesson 11. In lesson 11, we studied null and alternative hypothesis, basically the structure of hypothesis testing, and type 1 error versus type 2 error, and then 3 types of hypothesis testing. As for the basic structure, null and alternative hypothesis, I'm reasonably certain everybody remembers. As for type 1 error versus type 2 error, I cannot say the same. There will be some people who are still puzzled at least. But that's okay for now. We're going to talk about those in a little bit more detail in section 3 of this notebook. For now, let's just go to some example problems associated to the 3 types of hypothesis testing that we studied. Type 1, hypothesis testing for population means for known population standard deviation sigma. Now, what do you mean by known sigma? Isn't it really an outrageous assumption? Well, for interval estimation, this was indeed outrageous because we didn't really have a good idea what the population mean was, yet we know about sigma. That didn't make much sense, but for hypothesis testing, it does make sense because we have 2 hypotheses, null hypothesis and alternative hypothesis, but null, this is coming from past. So we can generally assume that a lot of study took place already and we have extensive data. And from there, we can assume that we have a pretty good idea what is the population mean and what is the population standard deviation. Basically the mu0 value and sigma 0 value. As for mu0 value, that goes to default or the null hypothesis. And as for population standard deviation sigma 0, we're going to adopt it as sigma. So it makes sense. And structure is kind of like this: mu0 value, the null, and sigma value, and then x bar value, the observed sample mean, and n value, the sample size. And finally, alpha value, the level of significance. Another problem, a little bit more confusing, but the same deal. mu0, sigma, x bar, n, and finally alpha. Please remember 2 types of methods. You don't have to do both types, even though both have been more preferable. The method I prefer is critical value approach, and it goes like this. Set up the hypothesis, of course, and then the initial picture goes like this. Normal picture on the null, of course, and then we are looking for the critical value. Alpha here, 1 minus alpha there. So beyond this critical value, we have alpha. So 2% here, 98% here. What is this critical value? Once you find it, you can compare it with x bar value. And if x bar falls here in the blue region, which means close to null, you see null is quantified here at the center. Close to null, then null wins. Far away from the null, then null loses. So how do you find your critical value? And that's easy. Z-score is n minus center over SE, and Z-score you can look up from your Z table. 2% here, it'll turn out to be negative 2.05, and n minus center over SE, you can find your x value from there. Solving that equation, you get the critical value. Once you have critical value, you can compare that with the x bar, and in this particular case, x bar fell here in the blue region. So we accept the null hypothesis. close to null, so null wins. The second example here is an example that alternative wins. Initial picture is like this, same as before, centered around the null, and you're looking for the critical value. Once you find it, and you can compare that with observed sample mean, 3060. And it'll turn out like this. Far away from the null, so we reject null hypothesis and consequently accept the alternative hypothesis. I like this method because the decision making is straightforward. Graphically, it is very clear when do we accept null and when do you discard. Close to null, null. Far away from the null, then alternative. Another way to do this is to use probability value approach. Goes like this. Centered around the null, of course, and here is observed sample mean, and find out the probability that goes beyond. And if this probability is too large, then that means the conditional probability of making type 1 error is too large. So you cannot reject the null hypothesis. So we have to accept the null hypothesis. And if this probability value is small, then that means the conditional probability for type 1 error is pretty small, so you can reject the null hypothesis and accept the alternative hypothesis. So the probability value computation is not too bad. N minus N2 over SE, and then you can find out your z-score and look up the z-table and you can find out the p-value. But what's the conclusion? The comparison with type 1 error with the alpha value, good luck about that. If you understand all those, great. But if you don't, this method can be confusing. Now, the second type we studied is for binomial proportion. Everything revolves around these formulae. Proportion is now new mean, so centered around the proportion. And standard error is square root of p1 minus p over n. Important thing here is to use the null proportion here. Here's an example. We're talking about the blood types. For A types, so Rh positive A, Rh negative A, so adding up we have 42%. So we have initial picture, the normal picture centered around the null, 42%. So we have to use this proportion for your SE computation. Like this. Square root of p1 minus p over n. Here we use the null proportion. Not this one, not the sample proportion. We have to use null, as you can see from this picture, centered around the null, so we have to use null. And then once you find out the critical value, you can compare that with sample proportion, in this case 78 out of 150, which will be 52%, and then you can make appropriate conclusion out of this. The third time we discussed was population means for unknown sigma value. Testing population means for unknown sigma value. So unknown sigma value will have to use sample standard deviation, and that's going to be t-table problem. In practice, in practice for you, so for exam preparations or for classroom purpose, for you in practice, the important question is whether sigma known or unknown. Known, then you use Z. Unknown, then you use S. So T. But if you step outside of this, then if you step outside of the classroom, then you have another question. Is the original population normally distributed or not? If yes, then you can use the T analysis and you can do fine. But If no, then you can't. You can use student's t-curve. You'll have to use central limit theorem for large n value. So getting large sample size means more expensive survey, but you can't help it. You'll have to do it that way. Example is kind of like this. We have a data set, and those are coming from observation, some experiment. So there are going to be some white noise, so it must be normally distributed. And the null is here, 5.517, and the sample mean will give you 5.448 if you remember correctly. And you can do things like this. Centered around the null, or excuse me, wrong cell. This will give you a picture. Centered around the null, and you can find out the critical value. How do you do that? The same deal, t equals to n minus center over SE. So x minus this null over SE. SE is going to be s over square root of n, not sigma over square root of n, because we don't know sigma. And then compare that with the t-score from the t-table. 5% here with degree of freedom of 28. 29 minus 1, so 28. And then shade it to the left, so you have to put the negative sign there. So we get negative of 1.701 like this. Solving the equation, you get the critical value. Once you have the critical value, you can always compare that with x bar, observed sample mean, and you can make appropriate conclusion. Fell in blue region, close to null, then we accept null hypothesis. Fall in red region, far away from the null, so we reject null and accept alternative hypothesis. Okay, so much for review. And we're going to discuss the other sections in separate videos here. So see you soon. Stay tuned.